got his master's degree at Clark University in geography. So we have kind of like a full circle here. So I'm going to talk to you all about the fate of a mucosalivary droplet and lessons that I learned from a synthetic sneeze. And this work is supported by the NSF. So to start, I just kind of wanted to talk about myself a little bit and introduce myself to the whole physics department here. So I grew up in the Northern Virginia, Washington, D.C. area initially, and then I've always wanted to go to Virginia Tech as a child. So I went there for my bachelor's degree, and I loved it so much that I stayed for an additional 5 years for my PhD. So I spent a total of nine years at Virginia Tech, just in Blacksburg, Virginia, just in the middle of this Appalachian Mountain area. And as an undergrad, I studied a lot of droplet formation and interfacial fluid phenomenons. But during my PhD, excuse me, during my PhD, I looked at water entry dynamics of plunge diving seabirds. So this here is a northern gannet, and as it enters the water, it creates these air cavities and pinch-off phenomenon that, and one of the questions we were interested in learning about was how do they dive without injury? And then I also looked into other problems regarding how animals jump out of water. So I built this tiny robot and trying to answer how animals across scales jump out of water. But alas, after those 9 blissful years at Virginia Tech, I had to move on. So I went up to Philadelphia at Temple University, where I did my first postdoc in granular physics and biolocomotion. And here's really where I became interested in how lizards run up these inclined granular surfaces, or sand dunes, if you will, and how they basically navigate these complex terrains. And I approached this from a physics and engineering perspective in an attempt to basically understand why do robots do so poorly on surfaces such as this, whereas biological, like the lizards, can run very well. So after 2 years at Temple, I moved on, decided to go up north even further, and I reached out to Arshad about a postdoc. And at first, when we were talking, we were mostly talking about how worms move in granular sediments. And that's really what I was initially hired to work on, was how these worms locomote in granular substrates. But as we all know, COVID-19 came along and hit really hard and really fast, rapidly spreading around the world. And the current cumulative case around the world is 44.6 million. And this is just a world map where you can see all the active cases around the world. And so actually when I first started talking to Arshad, it was kind of in early February. And during that time, COVID-19, there were probably like 100, less than 100 cases of COVID-19 in the United States at that time. But worldwide, there was probably about 75,000 cases in that time. But as you know, like as time progressed, the cases rose very, very rapidly. And so this prompted Arshad to write this COVID-19 grant to really study how the coronavirus spreads through droplets. So I started really looking into the coronavirus, trying to read up on the literature, and this is what the novel coronavirus looks like. It's got these spikes that kind of pop out of this vesicle. What happens is that when it's inhaled or it gets inside the body, it latches onto your respiratory cells and injects its genetic information into the cells, and that's basically how it reproduces. So a common question that we get is how many viruses are inside a droplet? It's actually kind of hard to know. Many scientists are still trying to figure this out. But if we just consider the worst case scenario, if we have a randomly packed jar with spherical pieces of candy in there, 63% of this volume will be made up of the candy, and then the other 37% will be made up of air, or yeah, just air. So if we consider a lot of these droplets are said to be spread through aerosols, and generally aerosols can be around 10 micrometers in diameter. Excuse me. And so if you consider a coronavirus or a coronavirus size at around 0.1 microns, or about 100 nanometers, you can fit about 630,000 viruses inside a 10 micrometer droplet, saliva droplet. And a 10 micrometer saliva droplet is basically almost 10 times smaller than the width of a human hair. It's really probably the smallest thing you can see with a naked eye. But just so I'm not spreading fear, this is probably the absolute worst case scenario if you try to pack as many coronaviruses inside a single droplet. This is the worst case scenario. So how does this virus get spread? As many of you might know, it's spread through these droplets, and as an affected person breathes or coughs or sneezes, the droplets can fall and hit some surface where another person can touch, and then if they touch their face, their mouth, their eyes, or something, then that's one mode of transmission that the virus can spread through. The other way is through these atomized or aerosol droplets, which can linger in the air for a long period of time and subsequently get inhaled by an otherwise healthy person. And so when I talk about expiratory events, probably the most violent one that you can think of is a sneeze. And so when you sneeze, this is an example of a human sneezing. You can see the droplets just getting dispersed out very, very quickly throughout this process. And this prompted a lot of researchers, this group at MIT, under the direction of Lydia Boriva. She looked at how sneezes spread and move in the air with this turbulent puff cloud. And this prompted others to start looking at how do droplets spread when you just simply speak. In this group at Princeton, they looked at how the saliva breaks up into small droplets from your lips. And this, of course, prompted people to also look at how do masks block the droplets from spreading in the air. And so here's an example of a cough. If you're not wearing a mask, and over here you're wearing a one-layer cloth mask. The bottom right or bottom left, you have a two-layer cloth mask, and the bottom right is a surgical mask. And you can see that these masks, while they're not perfect, they can block a lot of the aerosols or droplets from going out into the ambient environment. But the one issue with all these human studies I'm finding is that they're very variable and extremely complicated. So for example, the scenario of this cough, if you look at the y-axis, if you can see the droplet, the visible propagation distance of the single droplet versus the x-axis time. You can see that one droplet from a single case can travel up to 0.6 meters in 0.3 seconds, or even the slower curve, you can see that the droplet goes up to 0.2 meters in half a second. So there's a lot of variability in human trials that make it really difficult to understand the fundamental physics of what's happening with these sneezes or with these expiratory events. So one of the main questions we aim to answer is, can we create repeatable human expiratory events? And also, what can we learn from these events? And the thing is, doing research during this pandemic proves to be a very challenging task, but we have found ways around it where, for example, my PI Arshad here is working on building a 3D printer with fellow citizen scientists here. And using this 3D printer, we can print like a face where we use to test a couple of different masks and see how effective they are at blocking these droplets. And we'll discuss that later on. Furthermore, we also take great care, a lot of caution when we do these experiments. We stay socially distanced. The CDC guidelines says 6 feet or 2 meters is appropriate. So here's Trin, an undergraduate in physics, standing 2 meters away from Brahm, who's a master's student in physics. So going back to the topic at hand, we're to answer these two questions, we first try to make a synthetic sneeze and then validate the synthetic sneeze with human data in the literature. And then we're going to start exploring how these synthetic sneezes create droplets and look at their landing time, their as well as their distribution on the surfaces of which they land. And also take a look at how a face mask might reduce the amount of droplets that get expelled. So to start, we wanted to figure out how to create these saliva droplets, because I guess that's really the first step we want to take is we're not going to use water that doesn't have the same properties as saliva. So we found that mucin is a protein that really makes saliva all slimy and gross. And inside a normal healthy adult, the concentration of mucin is typically 150 milligrams per 100 milliliters of fluid. But another problem would be that acquiring human saliva or human mucin can be pretty expensive. So what we ended up looking at is good old Bessie over here getting mucin from the bovine submandibular gland. So we purchased some mucin from a cow, and then we tried to expel it using a droplet generator, which is very similar to what you would see at a hair salon, a sprayer from a hair salon. So here's the droplet generator spewing the droplets, and you can see the puff cloud that comes out and the different trajectories that the droplets might take. And I guess the first question that Arshad asked me was, how big are these droplets? We got to make sure that this is really similar to a human sneeze or something. So I let these droplets fall on a microscope slide, and then we found that the droplets range from 10 to 1,000 microns. And it turns out that this works really, really well with, or matches really well with what we'd see in a human sneeze. So in this example, there's a dual distribution where particle diameters are about 100, on average, 100 microns and maybe 600 microns. So now, having seen that, we wanted to analyze basically how far these droplets disperse and what kind of trajectories do they take. And in order to do that, we process these images by drawing a boundary around the cloud. And then we can mark different parts of this domain. So we have our boundary, and then we can calculate the center, the geometric center of the cloud, the outermost boundary and the lowest boundary. And as you can notice, there are also many droplets that are outside of the cloud that go further than what the than what we can draw here. So we also marked the furthest visible drops, the furthest and lowest visible drops. And by doing so, we can, if we look at the center, geometric center propagation, it goes actually much slower than the furthest droplet or the furthest boundary. But we do see that the geometric center starts to asymptote around 0.4 meters from the source, whereas the outermost boundary asymptotes near 0.7 meters, and the furthest droplet can go beyond 1 meter easily. And when we compare this with human data in literature, we find that a human sneeze, we're pretty close to what a human sneeze would do. So this is work done by MIT and Lydia Barriga's group. And from these two images, we find that our synthetic sneeze is very close to what you would see in a human sneeze as well. And additionally, we found that the droplet speed is on average 3.4 meters per second, but 80% of these droplets travel less than 5 meters per second. And we find that our sneeze, our synthetic sneeze travels at around 5 meters per second. So we're definitely within range of what we see in an average human. So now that we've described our expiratory events and how we validated it, what can we learn from it? One of the first things we wanted to find out was in detail what kind of trajectories and landing times these droplets would take. And just to kind of give you all a quick refresher on in physics, we have two different types of trajectories, and actually this guy named Tartaglia in 1537 observed these cannonballs that would shoot up at some angle and then drop vertically down. Whereas nearly a century later, Galileo shared his idea on the parabolic trajectories that you see in your Physics 101 classes. And really the difference between these two is air drag. So these two geniuses probably had some idea of what air drag was, but didn't know how to quantify it. But now we do, and we know that air drag is largely responsible for this aerodynamic fall, as most people call it. Whereas if you have a perfectly symmetric parabola, then it's because of you have negligible drag. And the reason you have this is a couple of different reasons, but you can see that this is a shuttlecock from badminton. When you hit it at a very high speed, it starts to hit the aerodynamic wall and then fall virtually straight down. So you get this asymmetric parabola. Whereas for a basketball at a lower speed, you have negligible drag and you have a very symmetric parabola. This is largely dependent on the initial speed. So if you imagine this shuttlecock that's falling, falling under its own weight and gravity, and resisting it is air drag. As soon as these two forces balance each other, then the velocity stays constant. This is the terminal velocity. In other words, u infinity. So if the initial velocity is higher than u infinity, or the terminal velocity, you start to get these asymmetric parabolas. Whereas if your initial speed is less than the terminal velocity, then you get a symmetric parabola. So let's take a look at a trajectory in a droplet from our synthetic droplet generator. So from this video, you can see the droplets being expelled and then also falling. And to make it more clear, we took this video and we can stitch it together, basically giving it this long exposure time. And all the different colors here represent time. So if you have a very white color, then it means it's early time. But as it becomes darker and more orange and auburn color, then it's later in time. and you can see the droplets, the darker colors start to fall down. And you can see a bunch of different parabolic shapes. And it turns out that a lot of these droplets take this symmetric or have this parabolic shape, but then other droplets don't fit the parabola. So in other words, in this first case, there's no air drag, and these individual dots are tracing one of these droplets throughout time, and we're seeing that the typical equation of motions for projectile motion fits really well with our experimental data. But then some other droplets, the smaller ones, they start to deviate away from our parabolic trajectories, or from our projectile motion trajectories, which suggests that air drag is influencing their final trajectory. And really, we can draw this analogy between the fact that the droplets that follow the parabola very well is it's like the basketball, where you have the speed is lower than this initial speed is lower than their terminal velocity, but then in other cases, the initial velocity is greater than their terminal velocity, where these smaller droplets start to experience air drag. And likewise, if we take a look at our cloud as a whole, we can see that we start hitting this aerodynamic law, or at least the geometric center hits this aerodynamic law, very similar to Tartaglia drew in the 1500s. And once it hits this wall, it starts to fall very slowly at various rates, depending on what we're looking at. So if we look at the lowest droplet, this point here, it falls at about 2 meters per second, but the cloud center falls at around 0.5 meters per second. The biggest issue we've had in all of this is how do we see the smallest droplets? And that was really difficult to do with white light. So one of the strategies we took was using fluorescent tag droplets. So here's Ram here making a solution of our mucus rhodamine, our mucus fluorescent solution. And if you add the fluorescent tagging to it and excite the solution with a laser, then it starts to fluoresce with this orange, beautiful fluorescent orange color. And if you add a 532 nanometer filter, in other words, a green light filter, then these lights come out more prominently. And so to see these droplets, we use our droplet generator to expel the fluid onto a surface from some height. And we have this laser line that allows us to very clearly see the droplets on the sheet or on our horizontal surface. So our big question still remains, now that we can visualize the droplets really, really well, how long does it take for one of these droplets to land? So what we've done is we used a high-speed camera. We filmed the laser line and saw how the droplets started to build up along that laser line. So if we spray it from left to right, we'll see that the droplets will light up. And then from this video, we can calculate the volume per total volume over some time on the x-axis here. And we show that, well, early on at 0 time, there should be no droplets there. But after we spray it, we see that there's this fast increase of droplets landing on our surface, and then eventually starts to plateau off over time. So in terms of the landing droplet, if you consider, say, the number of droplets that actually land. So if there's 25% of the droplets land, how long does it take for 25% of the droplets to land on the surface? So we're looking at this point here and the amount of time that takes. So from here, we're seeing that at 0.4 meters or 40 centimeters, it takes about 2 seconds for 25% of the droplets to land. But for the majority of the droplets to end up on the surface, it takes between 4 and 5 seconds. So using this technique, we're really able to see how long it takes for droplets to land on the surface, depending on what height that we notice it from. And while that's great, we also developed a theoretical model to predict the landing time. So if we take this free body diagram of a cloud, and 3 forces that are really acting on this cloud is, first of all, the weight of the cloud, and then moreover, you have the force of drag and the force of buoyancy. And the most important parameters that govern these 3 forces are really the size of the cloud, the density, and drag coefficient. And so to really understand how the size of the cloud matters, we looked at the 2D projected area of this cloud, and then over time. And so if we look at this area, it starts to increase, and we have this transient region where it increases very rapidly. But after about 0.2 seconds, the cloud detaches from our droplet generator and starts to, the area increases very linearly. We're at this steady state regime. But the issue here is that this droplet cloud is very complicated. It's a very complex shape with turbulent interactions inside of it. So we make this common physics joke of a spherical cloud, and we try to apply this to our cloud. So what we end up with is using this area equation to find the diameter of our cloud, assuming that our cloud is a sphere. So the next step is, now that we know the diameter of the sphere and also the falling speed, we can plot them together, and all of these blue dots are the transient or the steady state regime. And all the gray dots in the background are the multiple trials that we collected, and also the transient regime is back here. So we're really interested in the steady state portion here. And what we find is that we can input different parameters for the density of the cloud. And we find that if the cloud density is 2.5% higher than the density of air, then our theoretical line sits right on top of our data. And then if the density of cloud is only 0.5% higher than the density of air, then you get a line over here. What we found is we estimated the density of our cloud, and we actually found that it's around 1.1% higher than the density of air, and it really matches quite well with our experimental data. Given this range, we find that our theoretical settling speed would be about 0.38 meters per second. And if you remember, the settling speed of the cloud experimentally was 5.5 meters per second. So our theory matches pretty well with our experiments. And so if we look at our landing times again, if we divide the height at which these droplets release by our theoretical landing speeds or settling speeds, we find that the theory predicts very well predicts our experimental data quite well, even given our spherical cloud assumption. And so really what we're finding is that there's this temporal guideline of at least 5 seconds after a sneeze. So you really have to make sure that the droplets fall and wait 5 seconds for the droplets to land on the ground. And the caveat you should really take from this is all done under very, very ideal conditions. So in a common room, like in the physics classroom, you might get ambient airflows of 0.2 meters per second. So this 5 seconds would probably change. You need to give the droplet some more time to really fall and land on the surface. So now that we know more about how long it takes for these droplets to land, we want to know more about the spatial distribution, or in other words, how far do droplets go and where do most of the droplets end up landing on the horizontal surface. So our setup, we have our droplet generator again and our horizontal surface with a laser line, and we change the height to correspond to different settings. So if you have, say, this conference room, we looked at the heights that correspond to, say, the height between a person's mouth to a table when they're sitting at the table, or the height from a person standing at a table to the surface of the table, and also the height of a person standing to the floor. So we test the heights of 0.5 meters, 1 meter, and 1.5 meters. So we're finding that the spatial distribution really depends on the height at which the droplets are released. So if we look at a height of 0.5 meters, we get our experiments show a distribution that looks a little like this. And basically the maximum occurs at around 0.6, 0.7 meters away from the original spraying source. But we also have this distribution with a exponential decaying form to predict the tailing end, and we show that this exponential decay works fits really well with our experimental data. Our fitted distribution works quite well as well for all of the other heights that we test as well. So for 1 meter high and 1.5 meters high. And just to highlight the differences between the heights, we showed, I'm plotting all 3 of these heights together so that each individual point is our experimental data for the corresponding heights, and the solid line is their respective fitted distribution or fitted curves. And you can immediately notice some differences. For example, at the higher heights, the droplets tend to shift backwards, and also fewer droplets end up landing on top of our laser line here. And from the fitted distributions, we find that more than 99% of these droplets land within 2 meters in front of you. In other words, less than 1% of the droplets might go further than 2 meters or just end up floating around in the air. And this really is equivalent to a single 14-micron droplet. And so if we look at the maximums of our distributions, we find that if we increase the height, then we see that fewer droplets end up on the laser line. So we get this relationship where if you increase height, then you have fewer droplets on the line. And likewise, if we look at this mean distribution, we see a similar relationship where if you increase the height, then the mean of the distribution starts to go backwards. And what that really tells us is that if you increase the height, then you get some more backwards diffusion, which means that these stochastic events start to increase over larger height. So in general, if you have more air time, this leads to more probability or more chance for the droplets to spread elsewhere. So now that we know more about this distribution, I know you guys are probably wondering, who's got the face mask and what does the face mask do to help us? And so here we have our 3D printed face with a standard medical mask, and the same thing without the mask. And with our camera, our high-speed camera, we show that you can Without the mask, a lot of the droplets come out, but with the mask, you hardly see anything, if anything at all. And this really just pinpoints one of the strengths of our fluorescent imaging technique, where we can see the smallest amount of droplets that end up landing on the floor. For example, here we have the distribution of droplets on the floor without a mask and with a mask. And in the semi-log scale, we show that we still can detect some droplets that end up on the floor above our noise threshold. And to put this in the larger context, the total volume of droplets that end up on the line, if you don't wear a mask, would be around 8.8 microliters. Whereas if you wear a standard mask, it would be 0.1 microliters. And if you wear an N95 mask, it would be 0.0035 microliters. And if you take this into account, if you just consider if there was one virus in a single droplet, this is a hypothetical case, strictly thought experiment. If you have one virus per droplet and a 10 micron droplet, if you don't wear a mask, then you end up with 16.8 million viruses on the surface, and just on that laser line. Whereas if it's more like a 100 micron droplet, then you would end up with 16,000 viruses on the surface. However, if you just wear a standard mask, you end up with significantly less viruses, where it's only 200,000 viruses on the surface if it was a 10 micron droplet, or if you had 100 micron droplets, you would end up with 280 viruses. And likewise with the N95 mask, we show how much more effective it is than a standard mask, and you get 7,000 viruses for a 10 micron droplet and 7 viruses for 100 micron droplets. So in summary, we used a mechanical spray and really tuned this spray to match a human sneeze. And we show that it takes about 5 seconds for these droplets to land on the ground from a height of 1.5 meters, which is about 5 feet. And more than 99% of these droplets land within the 2-meter range in front of you, or 6.5 feet in front of you, meaning that 1% of these droplets end up floating around in there or might go further than 2 meters. But one caveat for all these experiments is you should know that it was all conducted in ideal conditions with no environmental flow. So if you were in a classroom that had some flow, then it might take longer for these droplets to fall. But the main take-home message I want you all to have is, in addition to the spatial guideline of 2 meters, people can argue left and right about what this spatial distance is, but we really should start enacting some kind of temporal guideline as well, in order to better avoid droplets getting on your clothes or getting onto surfaces. But I think further studies need to be done to confirm what this temporal guideline would be. And also that wearing a mask reduces the amount of mucosaliva on the surface by at least a factor of 100. So after all that, you all are probably also wondering, where am I going next? And I just wanted to let you know that that is not a question, that is always a question that's always on my mind. So someone like Ram Sharma would wonder, what is the slope? And I'll just tell you, it's 0.58 north of the west, and with an R-squared value of 0.99. And then Arshad over there, I know he's smart, and he's asked me this before, how confident are you? And here's the 95% confidence interval that I'll end up on this line. So if you ever need me, you'll probably find me somewhere along this geographic region. And with that, I would like to conclude my talk. Thank you all so much for attending. I'd like to once again thank the NSF for supporting this project. Our paper on this topic is currently under review with our preprint link below over here. Thank you again, and I'll be happy to take any questions.
Thank you, Brian. Thank you. Thank you for explaining the physics of a droplet's lifetime. We'll open it up to questions, comments, discussion in a moment. But I want to, before I do that, I want to just share a public announcement message, if you like. And so, Brian, if you allow me to just share my screen, I'll do that in this case. And so here's my screen. I hope you can see this. And just as I have been working with Brian, with Trin, and with Ram, trying to understand this, we've been home, and we have been home with our families. And in this case, I've used every opportunity to sing the phrase of using a mask. And this is my interpretation from my son. So this is a simulation that my 9-year-old son wrote all by himself. And here it is. Thank you.
Nice, thanks.
Yeah, it was very good. Thank you.
So I had a.
Yeah,
Go for it.
I know you mentioned it at the beginning, but what was the size distribution of the droplets you were measuring?
The size distribution, well, we have a range of droplets for our synthetic sneeze, and it was between 10 to 1,000 microns.
Okay.
But we don't have a full distribution. Whereas that's something that we would really like to do in the future, just to confirm for sure that our sneezing apparatus works as well as a human.
Okay. Yeah. I
have a question. How did you estimate that percentage? Like you mentioned 99%, 1%. How did you quantify that you actually counted everything correctly? Like the 99% of the droplets actually land within.
Right. We did this using our fitted distribution. So our experimental data showed, basically we use a theoretical line that fit with our experiments. And then from that theoretical line, we can predict how many droplets land within 2 meters. And from that theoretical or the fitted distribution, we can find.
But did you assume some sort of symmetry? Because my understanding, you measure along a line. Did you assume some sort of symmetry of the cloud? Did this model assume something like that?
Yeah, that's a really good question. Actually, this is really just the volume of droplets that land directly in front of you, or whatever that ends up on the laser line. So this does not really consider the full distribution of droplets that land on the surface. So yeah, it's really just the portion or whatever ends up on the laser line, and that's all we can really do right now. But one of our future works.
I was just curious, and but did you take into account the volume of water, saliva that you injected or that you sprayed in this?
Yes.
Okay.
Yeah, absolutely. That's how we got actual volumes for.
Okay.
For it. So the spray really ejects about 0.75 milliliters of fluid, and then from that we can calculate some fraction or whatever fraction ends up on the laser line.
Oh yeah, I see. Oh no, I understand. Okay, okay. Oh, that's cool. Thanks.
Brian, how much? So first of all, really nice talk and really nice work that
Thank you.
the whole group is doing. How much variation is there in a person's sneeze? And the video seems to show that the majority of the droplets from the sneeze comes from the mouth. How much comes from the nose? And certainly the angles are quite different too. So you would think that the distribution may be different.
Yeah. That's very true. It's something that we kind of simplified in our experiments. So in an actual human sneeze, it really depends on the person. Some people just sneeze directly through their mouth. And I know as a child, I used to hold my nose when I sneeze, so nothing comes out of my nose, right? But in reality, some people do exhale through their nose during a sneeze. And yeah, that changes their angles significantly. And also, there's some groups in Japan and Korea where when you sneeze, you do this kind of backlashing head motion forward. And so they quantify that, that biomechanics of that and input it into a simulation to see how the droplets disperse through the air. But really for us, that's something we don't really consider is the motion. We simplified it to a single stationary jet that comes out of a nozzle. But it's definitely something worth pursuing, where we also consider the angle at which the fluids are ejected from, and also think about, saliva or mucus coming from your nose as well, because that's very applicable.
And you can talk a little bit about how effective it is if you have a mask just over your mouth and not including the nose.
Exactly.
Yeah, I mean, those are really excellent questions. And in some sense, Brian has focused on sneezes to focus on the most violent expulsion. And as you saw when he was talking, he drank off a lot of fluids. And so that is, again, because as we speak, we are spitting. And so if you look at the screen on which you're watching this video and you try and clean it, you will see a bit of smut on your hand. And so the question is here, if you like, Brian has focused on sneezes. And so you might sneeze once, you might sneeze twice. And in Brian's experiments here, he has done 20 sneezes when he was testing those masks out. But you can ask, well, you're drinking a beer with your friend, over the course of 20 minutes, have you expelled the quarter teaspoon of stuff which comes out in a sneeze? When you sneeze, if you collect the volume of material which is coming out, that is about a quarter teaspoon. Now, when you're speaking, it doesn't seem like much is coming out, but cumulatively, over a few minutes or half an hour, it may be similar. So these are all starting points. Germano, our program manager, whom I convinced or didn't, he was convinced before I was, I think, that this would be a great direction to go into, because we were initially in the pandemic mode, just trying to figure out a way to help people like Bill, who's joined this conversation here. Like what is pragmatically possible in this scenario? And we were doing simulations to begin with. And then we started realizing that we could model anything. We could model any possible situation without knowing the data. It was impossible to be sure what we were modeling. And so I think this is really a starting point. And I think, Mike, you raise an excellent question, like you change and so on. So we need more students. We need more time to do these things.
Yeah, Brian, great work. Very
thank you.
interesting data, which I think will be very helpful to a lot of people. There's also great interest in how long the droplets remain in the environment. So obviously you have the ability to model that as well. But it seems like, and I was surprised that 99% of them actually drop out of the atmosphere, which seemed like a high percentage to me.
Mm-hmm. Yeah, I was pretty surprised myself actually, but I find that while most of the droplets do end up there, you can still have these smaller aerosols that linger for a longer period of time, and that's only considering a sneeze. Whereas if you're talking, the droplet sizes are much smaller, and they'll probably linger for even longer than what you would see in a sneeze. So definitely something we should look into more is what kind of droplet size distributions we're looking at for different expiratory modes, and compare the aerodynamics of these droplets.
Yeah. From another study I was just looking at, it's all particles that are under 10 microns that are the ones that float around in the room for a while.
I can argue that it's under 10 microns actually. Or I mean, not 10, under 100 microns. We have, I wish I had, Arshad actually asked me to put this in my slides, but I didn't have enough time. But I calculated the settling speeds for droplets for just individual droplets across 10 to 1,000 microns. And we're finding that even 100 micron droplets would settle very slowly over time as well. I'm trying to remember what values I had, but yeah, 100 microns can easily get picked up by some turbulent flow or something. It's not air drag will not be negligible for those scenarios.
So we, for example, modeled droplets which are coming out with different sizes, with different interactions, stochastic interactions, and they easily get up to 30 seconds, 1 minute, as soon as you start going even as large, if you like, as 100 microns or as small as 100 microns. So by the time you get to 10 microns, they can stay there for a long time. It's a very small fraction of the amount which is coming out. But again, that very small fraction can contain certainly enough viruses to be potentially interesting. We don't know, in spite of all these years of work and infectious disease on 6 months of work in our disease, how many viruses do you need to infect somebody? Nobody knows that yet. So one has to be cautious about extrapolating that one droplet hits you and that's enough versus hundreds hits you.
Right.